So, yeah, so we were discussing over approximations of behaviors of programs or any kind of systems that you want to use logic to model them. So so consider this program. Okay, so the program on the left side here, the swap program. And just for a moment, yeah, ignore all the pre and post and so on. So the program P1 consists of this, the input output behavior, as we model, as we used to. So it consists of these behaviors. I mean, the behavior consists of these input output pairs that are shown on the left-hand side. Now, on the right-hand side, I have a program which does somewhat something. It has, yeah. So for x is equal to y, when the inputs are when the x and y inputs are equal, then it does nothing. Okay. Otherwise, it assigns some arbitrary values. X, star. Let's assume that star denotes any value. In this case, I'm picking natural numbers. Okay, so it assigns anything. Okay, so I define. Okay, yeah. So the program on the right side, P2, is said to be an over approximation of the program on the left side. That's because the program on the right side, the behavior, it behaves, yeah, the P1, every behavior of P1 is also included in P2, so the P2 has more input output behaviors. In this case, if x is equal to y, the two programs behave identically. If x is not equal to y, P1 is more constrained, okay, as it swaps, whereas P2 assigns arbitrary values. So there's some comment there. Okay. Yeah, but in any case, good. So it's communicated. It's good. Yeah. So do you see what I mean? Yeah. So P2 is an over approximation of P1, and because if you consider in terms of the formulas, if you used SSA like I demonstrated in the previous class to model the behavior of these two programs, then as formulas, as conjunction of these individual SSAs, then this kind of a situation when P2 is an over approximation of P1, the formula phi P1 implies phi P2. That is, every time the input out behavior that is characterized by this formula phi P1 is also included in phi P2. So why would you want to do this? See, for this, at least is the definition of an over approximation clear? Maya and Harsh?
Sir, so over approximation is like one of them like is the subset of other, like in terms of behaviors.
Correct. The over approximation includes more behaviors, okay?
Okay.
More yes, more behaviors than what it is. So in the behavior of, yes, it is less constrained as far as its input-output, behavior is concerned. So in terms of the formula, we say that the formula modeling the behavior of a program, okay, of an over approximation is weaker in the sense that it is less constraining. Because it's less constraining, it includes more things in its behavior, specifically for things that are not, in this case, for things that are where the inputs are not equal. Both its swapped value or any other value, as a matter of fact, is fine. But why would you want to do this? See, in this case, if you're interested in proving this property, in this case here, what we are, the specification says what the property that we wish to show is that if x is equal to y in the beginning, then after the program is executed, x will be the same. So with respect to that expected property, the program P2 so behaves the same way as P1. That is, as long as the inputs are equal, the two programs behave the same way. Therefore, sometimes, depending upon the property that you want to prove, if sometimes you may you could as well use the program P2 instead of P1. Okay? Or in general, in this case, I constructed it somewhat artificially. So if I could transform this, a program, apply some transformation of my original artifact, in this case program, and do it in such a way that I add the changes I make to that, it adds, more behaviors, then by taking into account, of course, you will have to do it by, the motivation is to do it in such a way that the property is usually is preserved. So in general, if you add behaviors, then if the property that you're interested is still holds for the over approximation, then it also holds for the original program. Correct? So in this case, specifically, with respect to this pre and post, that pre-post specification is satisfied by the program P2, then it is sure to hold for P1 as well, because whenever this verification condition that we checked for the program, it holds good for P2, which includes more behaviors, then it has to hold good for the behaviors of P1, P1 as well. That's the the property that is true for over approximations, and that's why I'm saying that you could use P2 instead of P1 to prove that property. If you prove the property for P2, then you can also conclude the property holds good for P1. But of course, the reverse is not true, that if the property fails on the over approximated artifact program, then you cannot conclude. Now, for example, the previous property that the earlier specification I had was if x is less than y, then y will be less than, in the post condition, y will be less than x. Will not hold good for P2. Okay? Therefore, this transformation, this over approximation cannot be used to prove the earlier property that I had. But if the property is, in this case, it's somewhat weaker than this thing, then you may be able to do it. And this is a classical technique that is used in formal verification. Okay, not just for programs for anything. You can use it for even for DNN. For DNN, this is a classical technique or trick that can be used, and yeah, so that's what I said. If you can prove a property for P2, then it is true for P1. But if it fails for P2, nothing can be concluded for P1. And although it is not, in this case, even the original program itself is quite simple. Therefore, you may question as to why exactly you want to do this particular transformation. But in general, when you you could do certain transformations such that the resulting program that you get is an over approximation. Sometimes those transformations might make the formula simpler, and even its verification simple. Formula more compact sometimes. Therefore, the verification problem complexity will be simpler on the over approximated program. But of course, the over approximated, you have to first establish that indeed whatever replacement program that you use, the transformation that you use, is indeed a valid sound over approximation. Okay, but once you prove that, then you could prove any property of the original program using the you can use the over approximate program to prove it. And if you are lucky and if it succeeds, then your verification problem is simplified. So, for example, even in this case, here, well, yeah, I mean, in this case, you could say that there is probably not much of an advantage in actually using this, because in both cases, the theory of equalities can actually be used. And of course, in this case, I can make a kind of a very roundabout claim. Well, this program has 3 instructions. This one, of course, has a conditional thing, but in both arms, there is only 1 instruction. So maybe the formula is simpler, something like that. But it is not a very interesting transformation that I have made here to save any complexity. But in general, sometimes you can think of clever transformations that you can apply by looking, and these transformations are usually guided by the property that you want to prove. So if the property that you want to prove is with respect to the property, maybe you can think of some clever transformations that you can apply to your original program, such that those transformations will only add behaviors. Then you can use this technique, and you will see that we will use this. This is one of the techniques that will be used to simplify or to scale up the verification of, in particular, ones that we're interested, DNA verification. And this has been also used for scaling program verification as well. Any questions? I thought there would be one question, obvious question. What happens if you're on your over approximation that the property fails? What do you do then? Then you'll have to think of course, you cannot conclude anything, but you have to think of some other over approximation, okay, that fits your property. But there are other techniques that we will see. There are things called, you have to look at, maybe then what happens is usually that happens if you're added too much behaviors, okay? So then maybe you will have to refine the over approximation to eliminate some of those behaviors to get to a less coarse over approximation, okay? You have to try less imprecise over approximation. But the motivation is that usually you use those transformations that will be over, so as to make the resulting program, the model of that one will be, so that it will be less complex than the original one. Okay. Let me now, yeah, so this I've already discussed, the branching program, so I am not going to repeat this. So now we'll come to, so we have looked at, straight line programs, how to verify them, and any questions on this, on the way that I extended the derivation of the model using static single assignment to branching programs. Well, I assume that you understand how this kind of merge that is used, okay? So that's the one that is important. So there are two ways to reach, okay? Especially this one you have to understand, okay? So there are two ways to get to this point, okay? So one is by the case when x is less than y, then you assign, make this assignment. Otherwise, you make the other assignment z is equal to x. So what you have is now you will introduce a merge variable, a new variable z3, which can either be z1 or z2, depending upon whether x naught is less than y naught, or the negation. And your post condition will then be expressed in terms of the merge variable. So for every if then else, you first derive the the behavior of the block of the then block and the else block, and then assign to those two separate variables, and then you will introduce a merge variable for each of them, and then you take care of the two branches, two ways in which you can reach this particular point. Okay, and that's what you do. So, any questions here? Okay, so then I'll move on. Okay, so now the case of what do you do with programs with loops? Okay. One approach you can do is, so here is a program which just increments x by 2 until it reaches, as long as some condition holds good. So in this case, since it is incrementing it by 2, then if x is assigned some initial value, which is whatever the value is in y, then it will be even. If it starts with an even number, the initial value is even, then so will be the value of x after it gets out of the loop. So suppose that's the property that I'm interested in checking, which is true for this program. So one way of doing it is the simple way. I mean, if you want to, then you just unwind the program. Okay. Then once you unwind the program fully, unwind the loop, unwind the loop in the program using series of nested if-then else's, which is what I've done here. Then you can, certainly once it's fully unwound, you can use the earlier method, since on this unwound program, which is a loop-free program. Okay, the same way that we did, because this is now just a bunch of if-then else. So you could, so you can reach this point post the point at which you want to prove this property post in several differences. So there will be several branches, and there'll be a merge variable here that corresponds. So each of these things will have several intermediate variables corresponding to the number of iterations that you will do. And after that, you will merge them all into a, collect them into a single variable, and then you will do it. Okay, so that's one way that you can do. So what is the disadvantage of that, Maya?
Like this would work well if you had a for loop which you know will terminate. Like you may not know if it terminates.
Yeah, termination is one thing. Of course, if it's non-terminating, then you can never use it. That's certainly true. Even if it is terminating, you mentioned for loop, okay? So that you should know how many times to unwind it, isn't it? Yeah. So otherwise, how will you know? So the number of times to unwind, you may not be statically determined. Yes. So like Mia said, so if you know it, in this case, you know that there are at most 10 iterations possible, right? Therefore, you know that after 10 iterations is the worst case number. But in some cases, you may not be able to determine that statically. Then it will be uh, difficult to implement this method. Now, even if it can be determined, I guess that's what you meant, correct? So when you said for loop,
Yes, I meant like you had nice from a 1 to 10 or something like
yeah,
that.
1 to 10 kind of thing, or yeah. So even if it's not a for loop in while, in some cases while loop also, you may, but you may be able to determine the number of iterations, but determining the analysis that you require to determine the number of iterations itself can be as difficult as what we're trying to do. Okay, the program verification. You mentioned termination. Okay, termination. Analyzing a program to prove whether it terminates or not is doable. Okay, but in general, of course, it's undecidable to check termination. It's doable, but it is quite difficult. Similarly, analyzing the program to determine the number of times that you need to iterate is itself quite hard. But it can be done. But even in even those cases in which you can, like how Amir pointed out, for simple for loops, which structurally it is very clear the number of times that you will iterate. Such a technique will not scale, okay? Because your program will be can be quite huge. Now, for example, this 10 was 10 to the 6 or something like that, and so you will have a huge nested if then else. And since the size of the formula in terms of that you derive using SSAs is very much dependent on the number of behavior, there is an exponential number of branches that you have, and the merged formula will have a disjunction which is exponential in the number of branches. Okay, so it does not scale. So there is this question: how do you do it? But before I tell you, a loop invariant is a technique. Okay, is one technique that can be used for handling loops, for dealing with loops. But before that, I want to raise this question: if it is useful to unwind even fewer than the actual number of times. Okay. So maybe you don't want to, it doesn't scale if you have to unwind it completely, but is it useful to just unwind it fewer number of times than the actual number of iterations? Then, and check your specification on that. What do you think, Harsh?
Yeah, so I think we should be able to use induction or something like that on small.
Yeah, you're right. So you're ahead of the thing. So you could, yeah, a loop invariant is exactly the idea there is induction. Okay, but here what I'm saying, the question that I'm asking is, if it is, if I say unwind it only twice, will it still be useful, the program that I get? Will it still be useful to check this property? What does it mean even to check for fewer unwinds? Here I had dot, 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 dot. Okay, instead of dot, 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 or more specifically, let's suppose that I do this. Here I have unwound it only twice.
In this case, like it makes sense because like it is even all along the loop. Like this condition kind of holds all along the loop, so it makes sense to unwind it fewer times.
Yeah, but what is the conclusion that you get? So suppose I unwound only twice here, okay? And then, so first of all, I'll first define under approximation, then I'll return to the question. So here what I did was I unwound it twice. And then I'm assuming at the end, see, I'm putting a statement called, okay, now I assume that X is, I get to this point only if X is the negation of the loop condition holds. So that is X is less than or equal to 10. So if I derived, what does this program actually denote? What is the relative to this behavior? What is this program that I have here? The behavior of this program. Okay, so let me give the answer. So what does this, if I use the SSA to model this program, in the sense that I will start with X naught, Y naught, and I will do exactly what I did for the partially unwound straight line program. And if I used SSA, this is what I would have. So there are, so this is the result of one. If I unbound once, x1 denotes the result, the value of in X after one iteration. X2 denotes after two iterations. And if indeed after 0, 1, or 2 iterations, I end up exiting the loop, which is what the condition, this assumed condition here is saying. So it exits when X is, I'm sorry, gray, this should be less than. So there is a mistake here. Okay, no one noticed that. So I should have used the negation of the loop condition, which is what I meant to use there. So read all the greater than symbol here as less than. So that is the negation. So the negation of the loop entry condition is X greater than or equal to 10, which is what I meant. Okay. So what does this program? I mean, even without so this is, in this case, it's called an under approximation. Just like we computed over approximation by adding behaviors, in this case, if I just modeled it after two, by unwinding it only 2 iterations, what does it include? The behaviors, it includes only those input-output behaviors for which the loop gets exited after at most 2 iterations.
Yeah. So like this could be used if you find something false for this under approximation, then definitely it does not work. But if you find something true,
yeah, that's why. So that was the answer that I was expecting. Okay. So when I asked the question, if it still be useful, so yes, even for this thing, if the property, in this case, I kind of changed the property that I'm trying to prove. By the way, Harsh, does this program satisfy this pre and post condition that I have?
Not always, because like let's say X is 1 and Y is 1. Then
Correct.
after
Okay,
some
so for
iteration,
odd, it does not. It does not. So I deliberately did the change. Okay, it's to exactly illustrate what the comment that you made pointed out, that such under. Okay, first of all, do you agree? Do you know what I mean by under approximation? Just like over approximation, added behaviors. Under approximation in excludes certain possible behaviors. In this case, those behaviors for inputs that take more than two iterations, but it includes exactly all those behaviors for which the loop get exited in at most two iterations. So just like you guys pointed out, so under approximation is still useful, even though it doesn't model the behavior, it doesn't model all possible behaviors of your original artifact. It's because if the property is violated on the under approximation, then it's a bug. And like Harsh pointed out, so if you took the formulas, the conjunction of all the formulas in curly brackets, okay, which makes the model of the under approximation, which defines the under approximation, and then you try to prove the pre and post and derive the verification conditions, then any satisfying instance of the verification condition would be a violation of the program. In this case, it would get violated, for example, for x is equal to well, actually, so for example, what would be the thing? So what are the input-output behaviors for which this loop gets exited in at most two iterations? Amaya? So if
could you repeat the question?
Yeah. So if I model this and it, as Harsh pointed out, it does violate. So I'm saying, what are the violating instances where this property is violated after two iterations? So remember, the way I'm doing is y can take any value. I'm not constraining any. The initial value is unconstrained. Okay, it can be any natural number. So for what value does this get? Does the loop get exited without iterating 0 time, for example?
Any odd number.
Any odd number greater than 10. Correct?
Yeah.
Greater than or equal to 10. So for 11, 12, 13, etc., those things are certainly included in the violation of this under approximation. So is if x is equal to 9 and x is equal to 7. For those two, I mean, if y initially was either 7, that is x also, since x is equal, we assume x is equal to y. For 7 and 9 also are some instances for which this under approximation would fail the property. Correct? Because for 7 and 9, they take iteration 1 and 2. Okay. So anyway, so that is just check. So, but the point you guys have understood that under approximations are also useful to check as good debugging devices. Okay, and yes, so loops are handled in two different ways. One is, of course, the full unwinding, and it will not work for anything but very short, short, and simple programs. Okay, and it certainly does not work for programs that don't terminate and for which the number of iterations is not cannot be easily determined. But under approximations as bug hunting devices are very useful. Okay, and so you could unwind it up to some number of iterations until the formula gets too big to be handled by an SMT solver. So, and you could check. So at least after, if that does not give rise to any violation of the property, then at least you know that the program does not have any bug up to those many number of iterations, which is interesting. And if it does, then at least then you know that there is but you may not be able to find very deeply embedded bugs of programs, but for shallow bugs, this method of under approximation, of using under approximation, in this case, the way we under approximated was by unwinding it for fewer number of times. It is still useful in practice. And this method of, so is what is called an instance of bounded model checking. Okay, and don't worry about the terminology, but you kind of get an idea. So this is what model checking a program is. One way model checking is using symbolic logic. Okay, symbolic model checking is using symbolic logic to model artifacts and programs, and then checking them, checking certain properties of this kind that we are doing. These are called safety properties. Okay, and this method is called bounded model checking because you're only checking it for up to a certain bounded behaviors of your original program. Okay. So, but there is this question: is there a way to verify loops? Still, the question of verifying loops completely. Okay. And someone, I don't know who it was, whether it was Ameya or Harsh, who said use the technical term induction. Okay, so in what sense do you mean? You used induction. When I asked the question if an under approximation could be used, you said induction. Who said that?
Yeah, it was me, Harsh.
Harsh. Okay, so what sense did you mean?
Yeah, I meant like something like if it works for small numbers, and it works for like sometimes, like a lot of the times, if a bug happens, it can be detected for small examples. So if it works for the small examples, it is likely that it would work for bigger ones.
Yeah, but that's not exactly what induction is. So yeah, so
those small examples to prove that you could you sort of combine them to see if
okay, so that's kind of the idea. So the loop invariant, you will see somehow if you could, from a proof of I mean, induction, mathematical induction really says, okay, it works for 0 iteration. Okay, if somehow you could, assuming it works for all behaviors that take up to I iteration, number of iterations of loops. Okay, if we assume from that, and then you check that it works for behaviors that take I+1 iterations. Okay, so you'll have to do that kind of a general inductive proof. Okay, assuming that it works for up to all behaviors up to up to iterations that take I number of, loop exits up to I number of iterations, you need to then check in general that it works for I+1. Okay, that is, I guess maybe that is the where you were leading to. Okay, and that is how you, that's the idea of induction that we use for coming up with a method to verify loops completely. Okay? And loop invariance is a concept or a crutch, that important concept that can be used to make such inductive proofs. Okay? And that's what we will see how next. So what is loop invariant? So what is it? Okay. So let's say I use the same program to illustrate. So, so a loop invariant is, here is a program, the same program. A loop invariant is something, it's a predicate or a condition that we denote by I, and it's usually associated with the head of a loop, right at this kind of a point, where what I've shown here. Okay, such that the following conditions have to hold. Okay? Now, for example, in this case, yeah, I mean, so what is the argument? Hirsch said, pointed out, you could use inductive argument. Okay, if you were to use the inductive argument, what would it be? Okay, how would you express it to prove that this thing, if you assume that y is even, then when you exit the loop, it is always the case that x is even. Okay? Argument is, so this property, even that x is always, this condition x is always even, holds, okay, at this point, because it holds the first time you enter. It holds at the. I'm hypothesizing. I'm claiming that x is always even at the head of the loop, regardless of how many times you iterate the loop, which means that it holds good the first time you get to that point, correct, right? Because if y is even, and after you assign x is equal to y, x will remain even, okay, at the beginning. And second condition, if you assume that you start at the start of an arbitrary iteration of the loop, if you start with the condition that x is even, and if you enter the loop and the loop condition holds good, and you execute the body of the loop, which in this case has a single statement, then that condition that you have hypothesized will hold good. Okay, after any number of iterations, if the condition holds at the head, and then you execute one more time, it'll hold. Such a condition is what is called a loop invariant. Okay, it's a property of a loop. So it has to hold good. The two conditions are initiation, that I should be true the first time you're at the head, which is true in this case, correct? And the inductive case. If I invariant, the loop invariant is true, and that is all the variables, the values of the variables are such that the loop invariant holds, and the loop entry condition LC is true, then I must be true after you execute the body once. That is, the body is, in this case, yeah. So for the body, you just have to prove this. If you assume this precondition, I and LC, then I has to hold good after you execute the body. Okay. So you can see now how this can be, this is what you're doing here is exactly an inductive proof. It's just that inductive proof of programs applied to programs, and the induction is being done on the number of iterations. It is an inductive proof on the number of iterations it takes to execute the loop. Okay. So by proposing a loop invariant, then you have pretty much kind of reduced. Okay, so this is, yeah. So after that, yeah. So in that sense, a loop invariant itself represents an over approximation of of the loop. Okay. Finally, there is, yes. Okay. Before that, so now you have this loop invariant is any predicate that satisfies these two conditions. So with this, you can now prove the post property. Okay. How? Because it loop invariant holds good at the head of the loop every time in every iteration. So if yeah, in the last iteration, if you can use that loop invariant and the negation. When you exit the loop, it is the fact that the negation of the condition also, that is x is greater than or equal to 10. If you can use, then you can use that loop invariant and x greater than or equal to 10 to prove that your post condition holds true. That's the exit condition. So there will be effectively three conditions that you will have to prove. First, of course, you have to hypothesize a loop invariant. That's the clever aspect. Okay, that is something that the verifier, the person who's verifying, is kind of assisting. It is something that the verifier has to propose. Once that loop invariant is proposed, then you will have to check that is indeed a loop invariant, okay, by checking these two conditions. And if it is indeed a loop invariant, then you can check the exit condition. So this is one way. The inductive proof is a way that you can do without an actual unwinding of the loop. Okay. So is that any questions there? Is that idea clear?
Sir, could you repeat last part about like loop invariant represents an over approximation?
That I will get to. So, but at least do you get the point? If you propose a loop invariant, then the verification, you can reduce the verification problem of verifying a program with loop into these proving three verification conditions, okay, each of which does not involve a loop. The first part is that you have to prove that the predicate that you're proposing indeed a loop invariant. For that, you will have to prove that the part of the program, starting from the beginning till you enter the head of the loop, okay? So that part, this part here, that's like a pre and post, okay, using the part of the code that occurs before the program, okay? So let's assume that does not have loops. Of course, if you had that also had loop, then you can apply this, assuming that every loop has been proposed, for every loop you've proposed a loop invariant. So that is one part for which you can use the earlier method. Then you do this inductive check by just proving a pre and post property for the body, okay, like I've shown here. So you've eliminated this loop, okay, and then reduce the problem of proving a pre and post for which the earlier method can be used. And then you have to prove one other condition which I have not shown here, the exit condition, which I will show when I illustrate this example further, which is that if the invariant condition holds good and the negation of this entry condition holds, that is I and not LC, implies the post, okay, which is a simple formula that you will have to prove. Okay, so that is the idea. Okay, so that part I hope you understand, correct? I mean, do you? So
Yes,
is there any doubt
I
there? Yeah. Okay. So now, I will now get to the nuts and bolts as to how exactly you will do this. So another way to view this is, like I've said here, loop invariant represents an over approximation of the loop. What do I mean by that? That it includes that, after all, it's a predicate, correct? It's a predicate over all the variables, the program variables that potentially get modified by the loop during its execution. So it includes the set of all possible values actually assigned for the variables during all iterations of the loop, including the zeroth loop, that is at the beginning, and the last iteration. So for example, even of x, that's the loop invariant here. Okay. So what are so x is the only variable here that is getting modified, okay, because y is never modified, so y is remains the same. So I mean, even of x, the set of all values that even x satisfies is all even even numbers. So in this case, it includes all even numbers. Yeah. So indeed, in that sense, it is an over approximation of the loop. So therefore, what you can do is you can replace this entire loop with this kind of an assignment. Okay. So after this, if you know it's even, and since you know that even also holds to here, so you could just replace this. So here, this is kind of an assignment that I'm making here. Okay, I'm saying, oh, assign x to any value that the loop invariant satisfies. Okay. That's the assignment that I make. It's kind of a, just like I made x and y is equal to star, where I assign it to arbitrary. Here, I'm making a constrained arbitrary assignment. Okay, I'm saying, oh, x can take any value x prime such that x prime satisfies even. Okay, and then if I exit the loop, okay, assume x, yeah, then it'll be even. So in that sense, the loop invariant, okay, so if I include the loop invariant and yeah, so it includes all those things. Yeah, I mean, it's an over approximation because it may it doesn't precisely capture the exact values that they they take. Okay, so for example, x, the fact that x is less than or equal to x is less than or equal to 12. Okay, it's yeah. Yeah. So yeah, in that sense, okay. So it may it may not precisely capture the exact precise values that are assigned, but certainly any the values that are actually assigned during any of the iterations have to satisfy this particular predicate. In that sense, it's an over approximation of the thing, and you can use that now to check this. So after this, when you replace that loop by the loop invariant, to the variables that are modified, you assign those any values that are consistent with loop invariant, then you can then it becomes a straight line program, and then when you exit, you will have to do so. The exit condition that you are approving, once you check that it is a loop invariant satisfies initiation inductive next, then you can replace the loop with this, and then you check if your program, the loop-free program that you obtain by replacing it with this assignment, indeed satisfies the post. If it does, then you know that your original program with the loop is correct. Okay, so this replacement of this is a way of checking your exit condition using SSA assignments. That's all I'm I'm claiming. So in that sense, I'm saying that the loop invariant is an over approximation. It certainly is true of any value that is computed, any value that is taken by the variables during all the iterations. Okay, but it doesn't capture precisely the values that are taken. So that's why I'm saying it's a over approximation. You can always replace your loop with that assignment as per the loop invariant, and then through the original program using SSA. Of course, there is the additional responsibility of checking that the predicate that you have proposed as a loop invariant is indeed a loop invariant, for which you will have to do these two checks of initiation and inductiveness. And then once it is a legitimate loop invariant, then you can try to use it to prove your post property. Okay. But then there are so that is the that is the idea. So does that answer your question as to why it is an over approximation?
Yes.
Yeah. So what are some of the other loop invariants? I mean, predicates that hold good as loop invariants. In this case, even if X is good enough to prove. So are there any other loop invariants that you could propose?
Yes, X is less than 10, but it is not useful, I guess. Or more like X is less than equal to 12. That holds after the loop as well.
Yeah, but actually X is less than or equal to 12 is indeed not even a loop invariant, because see, Y can take any value, right?
Oh, okay, yeah.
Yeah.
So it was before the loop.
Yeah, you could say that either if it is either X is greater than or yeah, I mean, if it is, so there's a little bit more precisely what happens. See, if X can take any value here, okay, that is that is true. So if you could propose that if even it is even of X, or if and only if even of Y, okay, something like that, okay, that is certainly it is true, right? X is even if X is even if it is if Y is even. If and only if Y is even. That is another invariant condition, correct? So it kind of fixes your other things. So if here, if Y is even, then X is always always even. Yeah. That X is, or you can say that either X is greater than or equal to 10, okay, or it is even if it is only if and only if it is Y is even, okay. X is greater than or equal to 10. If it is greater than, if the initial value is greater than or equal to 10, then it can be even or not even. Otherwise, you can say it's even of X and yeah. So yeah, so those kinds of things. But the point that I'm making is that there are several different predicates that can that satisfy this this conditions of being a loop invariant. Okay, but not all of them will necessarily be useful for checking the given property. Okay, so you'll have to. It has to be the right kind of thing. I mean, it cannot be just like you were. The over approximation that that you meant to use, because if this check fails, if the exit condition that this check fails, that doesn't mean that your original program could mean that it doesn't mean that your original program is wrong. Your original program might as well be incorrect, but it could also be due to that the induction hypothesis, the loop invariant that you have proposed might be too weak, that it is over approximating the loop too coarsely, and that might be the reason why you're not able to prove the post condition. The same reason that your over approximation of your program failed earlier could be the reason as well. So then your task is cut out for you to find a better, stronger loop invariant that is adequate, that is a stronger predicate, that is a loop invariant, but that is strong enough to prove your property. Okay, so there is a bit of cleverness that you need, a designer's intuition that you need to propose something that is strong enough to prove the property. So in that sense, proposing the loop invariant is similar to over approximating the behavior of your loop. If you could somehow predict, if you could make up a formula that, what is the exact, what is the precise, if you were to characterize, the loop most precisely by a formula, what would be the formula? So that is kind of what is called the strongest loop invariant for this, for this problem. What would that be? And Hirsch, that is.
Sir, I have a question. Like,
sure. Yeah, go ahead.
Yeah, so like, can SMT solvers discover loop invariants by themselves, or like we have to provide it?
Yeah, Madhukar, do you want to take that question? So yes.
Yeah. So SMT solvers cannot give you loop invariants. The short answer is that they cannot give you loop invariants, but they can give you a lot of insight into what could be happening, and that insight can help you construct loop invariants. But it's a difficult task, and it's not very straightforward. It's not immediate that they can.
Yeah, it's not automatic. They cannot discover loop invariants automatically, but they could be a means to that end. For example, loop invariant synthesis is one of very popular and in applications. It's a area of research. So the idea is that you have to synthesize the predicate such that these two conditions are satisfied. Therefore, you know that checking these two conditions can always be done by SMT, which is what I have, I've actually, you agree with that, right? So was that Hirsch that asked the question?
Yes.
Yeah, so checking each of these conditions, just like once you've discovered checking the exit condition, which can be done using SSA and then deriving an appropriate verification condition, by exactly proving it for this program. Okay, do you agree? And then you have to check these two conditions separately. Each of that can be reduced into an SMT query. Okay, but beyond that, what is it that you have to synthesize a predicate So it's actually something like this. There exists. Yeah, that is why it cannot be done as first order SMT problem. So your problem is this. Does there exist an I, okay, which is some state to state? It's a higher order, okay, such that and your exit condition. So let me just say exit. So there exists an I such that for all x, comma y in this case, these are the program variables. Oh, I lose it. Ah, so here. Okay. So it's this kind of a formula that you will have to discover. So it's firstly a second order. So if indeed you have an SMT solver that can solve this, okay? It's a second order thing. See, that's why, so that's a simple answer for Madhukar gate. So first order SMT solvers cannot do this, okay? So your search is over an I, which is a second order entity, okay, which maps, not state to state, state to bool, okay. Correct? It's a predicate, okay? It's really a predicate that you are discovering, a predicate. So that's why it is outside of first order, predicate SMT logic.
Okay.
So, but you could search. I mean, there are various things. Okay, search tech where you could have a search method to somehow search for these I's, for wherein in some of the subtasks you could be using these SMT solvers for doing it. Yeah.
So in general, it is true that so as sir is saying, you can certainly check, given if somebody tells you that, look, here is a candidate invariant, you can certainly check using an SMT solver if that's actually an invariant or not.
Yeah, that is within the.
Yeah, sorry, sir, you're saying something.
No, that's all. Go ahead.
Yeah, so that immediately gives you a way to do it, in the sense that, if you write something which keeps spitting out candidates, then you have something which is a guesser, which can guess candidates, and there's something which is a checker, which is exactly an SMT solver, which can check whether a candidate is good or not. And now with a guesser and a checker, you're certainly good. You can think of this as an invariant.
Like guided search.
Huh?
Like guided brute force, something like that.
Yeah, if you have, if there is, so yes, rightly as you said. So we agree that, with a guesser and a checker, we are certainly there. Now the guesser cannot be, it cannot be guessing arbitrarily, because there are just too many solutions, and as in there are too many possibilities. And therefore you cannot have something which is unintelligent or which is not guided. So therefore a guided guesser is much better, and it's actually what is required if you want to do it this way. The better you guide it, the sooner you will get an
So for example, the guesser can, you can use maybe a TNN or something, or a machine learning box.
Certainly, why not?
Yeah, I mean, there are people who have done that.
Yeah. I mean, like, does there exist some Python package which can, like, or something like off-the-shelf software like which does it?
So there are tools that are called SIGUS tools, syntax guided synthesis tools. So the way they work is they use an SMT solver as a checker, which is what we just talked about, and they have a grammar in which they guess. So they come up with a grammar, and then they keep enumerating expressions in that grammar, and they check whether this expression satisfies all the constraints or not, or the next expression satisfies all the constraints or not. So you can define a grammar which is both good to have a space of solutions, but is also good in the sense that the space is limited and you can actually enumerate.
Okay. Like, do they work good in practice, or like?
They work, yeah. So there are guess and check techniques that work quite well in practice. I mean, yeah. So they are competitive, with respect to other techniques. You can actually write a good guesser and a smart checker. Yes.
Okay.
Yeah, but it's not the method. The method technology is still not mature. There's a lot of research going on.
Of course.
You can't go check, do a Google search, and then find a Python box to do it.
Yeah. Python may not have packages to do this.
So it has not reached that thing, but it is a very interesting research direction and problem that a lot of people have been, including Madhukar, who's doing that. Okay.
Nice. Like, where should I read more about this?
So if you want, so I think one good thing to read is this thing called syntax guided synthesis. You can look at some very early work on syntax guided synthesis, and that will give you an idea of the power of SMT solvers, which I believe is the subject here. I mean, how capable are SMT solvers? So that's something that you can find by reading about syntax guided synthesis, and they'll also talk about how you can synthesize predicates suitable for a task.
Yeah, but with respect to DNN, is there something similar?
Okay, yeah. With respect to, so learning it from. No.
I didn't even mean using DNN to learn. Okay, as opposed to things. So I thought there was one paper that we had. So there's a recurrent loop thing. So is there synthesis of loop invariants for?
So they also synthesize loop invariant, but I believe it's similar to how a SIGUS solver does it. So I think SIGUS, syntax guided synthesis would be a good.
That would be a good starting point.
Yeah, certainly.
Do that. Yeah. So that certainly is a very interesting and exciting area of research.
Certainly.
A lot of people are working on, and have any new ideas there? So one can contribute.
Yeah.
Okay. Like, this looks nice, actually.
Yeah, it's actually very nice, and it's magical because you're actually synthesizing something or you're constructing something. So the sooner you can do it, the better you can do it. It's actually very nice to be the capability of doing this is. But it's also the niceness comes also from the fact that it's a very difficult exercise.
So, like, how is this related to program synthesis? Like, is it like, could you also synthesize programs?
One can also synthesize programs. So you can, so let's say, you can, of course, program synthesis is a long way from here, but assume that, you have been given a program with some holes, as in there are some, so there is an if, but the expression of the if is not given to you. And then there are certain other things which are not given. Now you can synthesize these expressions. So you can fill holes in a program, and then you can perhaps synthesize an entire loop or synthesize an entire program. So step by step, you can make this more and more challenging.
Yeah. Nice.
Yeah.
This is nice actually. Like I got very interested here when I saw OpenAI's Codex. Like it could synthesize whole programs. So
True.
maybe like combining this with neural
Yeah,
network.
certainly. Yeah, so logic
might be
has a
really
lot
great.
of capability, and AI, of course, has a lot of capability.
Yeah.
And I think there is something certainly that can be done by using both of these things.
Correct. Yes. Yeah. Yeah, that's certainly interesting. Yeah, these are some of the things that I wanted to. So we'll certainly be working with over approximations, applying loop invariants. Whether we'll be doing use of loop invariants and over approximations and under approximation for verifying DNN to scale its verification. And when over approximations are a 2-course, what do you do? These are the kinds of things with respect to, specifically with respect to DNN and various versions of them. That will be what we'll be looking at. Okay. Now, if you want to branch off to something else, beyond that, that can be pursued if you're interested in doing something for your masters and so on. So certainly it's possible. I mean, if you want to do something as part of the thing, so that's something that we'll have to discuss. We have a much smaller class group this time in the course. We are still debating as to what projects we should be assigning. So the next couple of weeks, we will make a determination of that.
Okay.
So, whether that is possible as part of the project, the problem that you mentioned. So certainly it's an application of Cygus. It's not necessarily, Cygus is certainly an application of SMT, but not in line with the DNN. Okay, and so because this is about neural network and deep learning, so it has to combine, the project has to combine some of those two things. So we will see.
Okay.
Yeah, any other questions with respect to how loop is handled? Yeah, so the only remaining thing that I had was this. So then the loop verification can be decomposed in checking the following verification conditions: this initiation and inductiveness, and of course that you will have to then there's a check given the proposed loop invariant whether you can prove the property or not. For that is that is the exit condition check. For that you can use. That's also now one with fewer. You can use the previous method because you have one fewer loop. But assuming for every loop you propose a loop invariant, then you can replace every loop with its proposed loop invariant. So then what you have is a loop-free program for which the previous method, earlier method, can be used. And if that doesn't work, then of course you have your work cut out for you, and you will have to refine your loop invariants proposed, okay, to make it stronger, to fix it in order to make it strong enough to prove the problem. Yeah, so that is the kind of thing. So in that sense, it is very similar to using approximations for programs and refining them to get to the right approximation. It's applied to loop. Okay, so that's good. Yeah. There's no more questions. I'll